with the first speaker, Tom. Tom is going to start talking about the EXTP in the astrophysics skyscape, and I'm just going to give the microphone to him. All right, thank you.
Okay, so thank you all very much for organizing this. I noticed there's about 100 people online, and in most of the webinars I've been on lately, the attendance has been dwindling compared to a year and a half ago. So I think congratulations are due to the organizing committee for putting together a program and publicizing it well enough to get a lot of people to show up. So I'm going to talk about which EXTP science requires multi-wavelength partners, both simultaneous multi-wavelength data and just supporting data that come from other bands that are essential for interpreting the data, but don't necessarily need to be taken at the same time. Which facilities under consideration most benefit EXTP and other X-ray timing science. Which existing facilities are ripe for instrument upgrades that could help EXTP. And I'll address these with some scientific vignettes, so just short discussions of some science cases rather than going into detail. Some of the things I'm going to talk about, other people are giving full talks about later on, and I'm going to be focusing on rapid variability and accretion. All right, so first of all, let's talk about multi-wavelength timing. So if we look at an X-ray binary, this is Rob Hines' classic BinSim image. We have our X-rays coming from the inner accretion disk. We can have radio and infrared and optical emission coming from a jet. We can have optical emission coming from the donor star, optical and ultraviolet emission coming from the accretion disk, and then we can have absorption in a disk wind. And if we want to really understand what's going on with these systems, we really need to map out where all of the emission in all of the different wave bands is coming from. A lot of that can be best done with timing. Right. I think we've seen that you can have vastly different spectral models that give you essentially the same quality of fits to the spectral data, and therefore really need to use the timing data to understand what's going on. All right, so one of the things that we can do is if we want to understand the jets from these systems, we can look at longer wavelength timing data. So this image here is from the Casella et al. 2010 paper on infrared and X-ray timing in GX59-4. And what you see is that the infrared data in all three of the RXTE orbits lags behind the X-ray data by about 0.1 seconds. And what that seems to be telling us is the X-ray emission is coming from some very inner region, and it takes about 0.1 seconds for whatever disturbances are happening there to propagate up the jet to the region where the infrared emission is coming from. And infrared is especially good for this kind of work because infrared should be coming from the bottom of the jet, but it's a lot harder to produce the infrared emission from the thermal emission in the outer accretion disk. Optical emission can be coming from many different components. It can be coming from the outer accretion disk. It can be coming from reprocessing in the donor star. It can be coming just directly from the donor star, and it can be coming from the jet. So the optical correlations tend to be a lot messier. And then the idea here is that if you can get more bands going further out into the infrared, you can get more lag measurements. And generally speaking, the jet becomes optically thick somewhere in the near infrared band. So as you go towards the mid-infrared, you're starting to probe regions which are still optically thick. And in the standard Blanford and Kernigel model are coming from further up the jet. And so the lag should be longer. And by mapping out lag as a function of wavelength and doing that repeatedly for many measurements of the same system, you should be able to really map out the jet structure. And Federico Vincentelli is going to speak later with a lot more detail about this kind of idea. All right, now, if we look towards the future, what are some of the things that we need to watch out for? So one of the ways that we might want to try to get very high sensitivity mid-infrared timing data is using the James Webb Space Telescope, which should launch within the next year or so. Now, it turns out that the James Webb Space Telescope has one serious problem for doing this kind of work, which is its absolute clock accuracy. And so people who've heard me rant about this before probably recognize this image and probably snickering privately already. This is an image of one of the clocks that John Harrison built in the mid-1700s to try to win the longitude rewards from the British government for developing clocks that could be used to help do celestial navigation. John Harrison's clocks in the 1700s that would work aboard a wooden ship are about as accurate as the James Webb Space Telescope's absolute timing. So what you have to do to time James Webb data relative to other bands is to do some timing calibration. You need to have some targets that you know what their timing behavior is like and observe them from the ground and from James Webb, and then go observe your target. For ground-based telescopes, there's a couple of things that you have to worry about too. Sometimes the detectors aren't fast enough. That's starting to change a lot in the optical with electron multiplying CCDs. In the infrared, the detector speed is usually not a problem. But a lot of times the recording systems are not set up to deal with fast timing data. And that's, for example, why the mid-infrared instruments on Gemini haven't been used for this kind of work. The detectors are capable of doing the timing, but the kind of firmware between the detectors and the data that you get are not capable of doing it. And some ground-based optical telescopes don't have good GPS clocks on them to do the absolute time stamping. This is something that with 6 years between now and when EXTP launches, if our community gets together and pushes on it, probably can improve a lot for ground-based stuff. And as we start to think about future satellites that might go forward, a lot of times if you care about this enough at the beginning to make it an absolute timing requirement, it's not that hard to get it done. But if nobody pushes the idea until the design is too far along in development, then it becomes a problem. It's really hard to add requirements in after the fact. All right, so the next thing you could do is you go even further up the jet to the radio and sub-millimeter bands. This is from a plot from Alex Teterenko, who's also speaking later today, from a paper that came out earlier this year on MAXI 1820 plus 070. And you can see variability in X-rays up here, optical here, infrared, near infrared here, and then progressively longer wavelength radio data moving down, right? And you can see the variability is really sharp in the ALMA band here, and it's pretty sharp here in the VLA upper bands around 20 gigahertz in the blue and red points. As you go down to the lower frequency VLA data, there's still some variability and you can do stuff with that, but the amplitude of the variability is much weaker and the time scales are much slower. Right. So one of the big advantages of the radio is that you really know the radio is not coming from the accretion disk. And the other one is that there's a lot more space and frequency space where you can work. Right. So the radio data here is spanning a factor of 60. The whole optical and infrared bands together basically span a factor of 60. But you can do this with a couple of facilities in the radio, whereas you need a whole bunch of different facilities to do this in optical and infrared. All right. So what are we looking at for radio timing going forward? So remember, the variability is much stronger at the high frequencies of radio emission. The square kilometer array, unfortunately, only goes up to 14 gigahertz. And the collecting area in SKA1 is only a few times the collecting area of the very large array. So the SKA is probably not actually going to drive improvement in this area very much. The one way that it will help a lot is that it'll be in the south, and some of the interesting targets are too far south for the VLA. But in terms of what you can do for the sources where you do get data, SKA will not be a major advance. The next generation very large array, which is the proposed American big upgrade in radio astronomy, that would go from 1 to 116 gigahertz. And if all goes well, it'll have a significant number of antennas built by the end of the EXTP mission. So one thing I think that is important to think about is that the EXTP and the rest of the X-ray timing community should start pushing for NGVLA if they haven't already. The other thing is ALMA may have sensitivity upgrades, which may make it easier to do this kind of work. If dishes get added to ALMA, it may make it easier to subarray ALMA and do multiple frequencies at the same time. And even some of the millimeter single dishes are useful for this. So Alex has a JCMT proposal to do this kind of science. And I think Alex will talk more about the details of what can be done in this kind of work. All right, so now we also want to understand the outer accretion disks and the donor stars. And this is something where there was a lot of work done a little over a decade ago, and there hasn't been so much in recent years. But these plots are from a paper by Teo Munoz-Darius from 2007. I think it was part of his PhD work. And a lot of this, the methodology for this was developed by Kieran O'Brien about 20 years ago. So what you can do is you can look at, in this case, there's an X-ray light curve from RXTE at that time, and then Bowen plus helium-2 emission line fluxes and then continuum fluxes. And I think this was done with ultracam on the William Herschel telescope. And so the idea is that the Bowen blend, which is some carbon and nitrogen lines that are very close to where helium-2 is in the spectrum, and helium-2 are both probing high excitation regions that are being pumped by X-ray or ultraviolet light hitting some dense region that's at lower temperature. Right, and so what they were able to do is to look at where the Bowen fluorescence is coming from. Now, and they were able to find that there was a lag, and the exact details of the lag structure can help you map out where that Bowen and helium-2 emission are coming from. Now, they had to do this with an emission line photometry filter because of the sizes of the telescopes they had available at the time and the amount of time that they could get on them. But that's not ideal because you've got a couple of things going on. That you can have fluorescence from the outer accretion disk, and you can also have fluorescence from the donor star itself. And the fluorescence from the donor star itself will give you narrow components in the spectrum, which are kind of illustrated here. So this is from a paper by Rob Hines and collaborators in 2003. This is the one that gave us the first decent estimate of the mass of the black hole in GX39-4. And I'll talk about some of the problems with that work later. Right, and so if you look at this plot here, you have the Bowen blend, and you can see narrow components and broad components. And the idea is the broad components are coming from the outer accretion disk, and the narrow components are coming from the face of the donor star. And so if you really understand everything about this with fast spectroscopy, you could do things like understand what the flaring in the outer accretion disk looks like by figuring out which parts of the donor star are being shadowed. Right, and because there'll be different delays from the accretion disk to different parts of the surface of the donor star. Right, so you'd like to do this with fast spectroscopy instead of with fast narrowband photometry so that you can actually isolate the different components of the line, but we haven't had that capability to do this so far. Right, and then if you can reverberation map the stellar surface and figure out where the emission lines come from, that can help you really understand what's going on if you try to use the emission lines from the donor star to trace the motion of the donor star. Right, and that brings us to the next slide here. So on the left, we have the radial velocity curve from Hines's paper from the emission lines. And on the right, we have the same system from Mariana Haida's work using absorption lines when GX39-4 got into a really faint state. What you see is that Hines got the period right, but the amplitude of the radial velocity curve a little bit wrong. And he pointed out in his paper that this was a serious potential problem with the results. So he understood what was going on there. And I think he was probably actually the most skeptical person of those results for quite a long time until the Haida paper came out. And so the kind of the challenge we have is that the emission lines and the outbursts are a lot easier measurements to make than getting the absorption lines in quiescence because the systems are brighter then. But you have the systematic error that you have to deal with, which is that you don't necessarily know exactly what part of the donor star is giving the emission. And since you're not spherically symmetric about the center of the donor star with the emission lines, you're not tracing the center of mass's motion, you're tracing the motion of some other part of the donor star. If you can use timing measurements to map out where on the donor star you're measuring light from, then you can correct these and actually get the same quality of data. All right, and so then there's burst reprocessing, which probably requires data from all across the different energy bands. So one of the other things that you can do is you can see type 1 bursts, which give you a very sharp increase in the X-ray flux. And this is from another paper by Rob Hines in 2006. And one of the things they found is that the response function in the optical and ultraviolet to a type 1 burst seemed to vary a little bit depending on the orbital phase at which you took the data. And that may also be telling us something about reprocessing in the donor star. And then there's another bit of work which is quite interesting, which is there are some cases where you look at the type 1 bursts in the soft X-rays and you see a sharp burst, and you look in the hard X-rays, and this is a 30 to 300 keV data here, and you get a dip right at the time of the burst. Okay, and so in a lot of the cases when you have bursts in hard states, the hard X-rays shut off during the bursts. So then the question is, are you pumping soft photons into the corona and collapsing it, or are you blowing the corona out entirely so that you're not producing hard X-rays at all? And we don't know that right now. So one of the things that we're looking at in a project led by Nathalie Degenaar and Tom Russell is taking radio data and integral data over some lengthy periods of time on some radio bright neutron star binaries and seeing if the radio jets shut off in response to these bursts that quench the corona. All right, so now we want to talk about polarimetry. So one of the nice things that you can do with polarimetry with EXTP, taking advantage of both the timing and the polarimetry capabilities, is to try to understand what happens to the polarization properties as a function of QPO phase. And this is a plot from a paper by Adam Ingram and collaborators. And so you can see the X-ray fluxes will change, the position angle of the polarization will change, and the amplitude of the polarization will change. And how they change depends on what models you use, right? And this is probably only going to happen if you have some kind of geometric model like a precession to explain the QPO. In the context of some other models, you might not see these kinds of polarization changes. Now, one of the things that you want to understand is, do the position angles line up as you expect between what's going on in the polarized data and what's going on the plane of the sky? And are the effects following the inclination angles of the X-ray binaries in the way that you expect them to? So if you get a large number of measurements, are you seeing amplitudes and changes in polarization for QPOs varying with inclination angle in the way that the models predict? And in order to really do this, we need better measurements of both of these, especially the position angles. All right, but I'm going to talk about the inclinations first. So the inclinations are kind of nice because we sort of know how to do this. So this is from a paper by Andy Cantrell that came out 11 years ago, and he looked at the SMARTS data for AO620-00 in quiescence. So with the SMARTS data, they have these decades-long monitoring campaigns in very many filters of light. What Cantrell did by really digging into the data was that he realized that the accretion disk variability changes the colors, and it also changes the overall brightness of the light curve. And it does that in a way that also changes the amplitude of the ellipsoidal modulations from the donor star. Right, so he found that he could basically fit a model where he put in the ellipsoidal modulation from the donor star as one parameter, and then he could fit the accretion light with a bunch of other parameters, and he could get a self-consistent value for the inclination angle due to the ellipsoidal modulations. Right, and so he was able to do this because he had decades of data with very high cadence for the measurements, and many colors taken quasi-simultaneously, so basically right back to back. So how are we going to do this for more X-ray binaries going forward? So LSST will get tons of data on these systems, but I think one of the problems is that their cadence is typically about once every 3 days. And these 3 different plots overlaid on one another here are from January 12, 14, and 15 of 1989. And you can see within 3 days, you're getting some major differences in the baseline level for these light curves, right? So that may be potentially problematic to try to do this with LSST. LSST also hasn't really decided what the cadence will be for changing filters, but there's a good chance that it won't really be taking quasi-simultaneous colors. So we may need to push for LSST campaigns on certain parts of the sky that are more well-suited for this. Or there may be projects like BlackGem that can just go do this one by one for the individual sources of interest. But we do need to take advantage of the big data time domain campaigns in order to improve these the quality of the ability to do ellipsoidal fitting. All right, so now we can also think about going towards better position angles. So doing the position angles for the orbits is really hard. People have tried to just assume that you could get the position angle for the orbit from the position angle of the jet, but they're between the V404 SIG position angles for the radio data jumping around, and the recent Potanen et al. Paper on polarization in Maxi 1820. I don't know that that's really going to work very well. Probably a lot of the jets are misaligned and potentially jumping around. So what we want to do is figure out some other way to do the position angles directly for the orbits, and this is hard. So in one case, Cygnus X1 radio astrometric wobble can tell you something about the orbit, but this is hard to apply to other systems. The radio is tracing the motion of the massive object, which is the black hole in low mass X-ray binaries. In Sig X1, this kind of works because the donor star is more massive than the black hole. But in the low mass X-ray binaries, which are the bulk of the black hole X-ray binaries that we have, the donor star is much less massive than the black hole, so the radio wobble is going to be small. There are also some wind opacity effects on the radio positions that are kind of illustrated in this figure that can make it hard to do this even in systems like Sig X1. And the optical separations are really small, and the sources are kind of faint for optical interferometry. And then the other problem is that if you try to do the optical emission when the optical is bright, you're going to get some mixture of optical light from the accretion flow and from the donor star, and you have to figure out how to account for that. So I don't have a quick answer for that issue, but I think it's something that we need to think about in order to interpret the polarization data properly. All right, now let's talk about the fundamental numbers for stellar mass black holes. So if you talk to a relativist, they'll tell you that black holes are described by three numbers: the mass, the spin, and the charge, and that the charge is usually not interesting. But from a stellar evolution point of view, black holes have three numbers again. If you want to think about what do measurements that you can make of a black hole now tell you about the evolutionary history of the progenitor star that produced it. And for those, it's the mass, the spin, and the space velocity, right? And all three of these are interesting, right? So if you really want to understand this question, why supernovae explode, because supernovae are happening under this optically thick envelope, all that actually looking at the supernova tells you is the mass of the envelope and the amount of energy that got injected into it. So if you want to understand the internal dynamics that lead to these stars blowing up instead of just collapsing, you need to look at either neutrinos or gravitational waves, which can escape through the envelope, but those are hard. Or you need to look at the remnants that these systems leave behind and work back doing some detective work. And this is where we actually have the potential to really make some progress right now, is looking at the mass, spin, and space velocities of the black holes. Right, and the space velocity is basically telling us whether the explosion was symmetric and left a low kick remnant, or asymmetric and caused a high kick remnant. All right, so if we want to tie these parameters to stellar evolution, I think we're starting to see some trends developing. So this is from Picchiatri's paper from a couple of years ago, and you can see there's a rough anti-correlation between the potential kick velocity and the black hole mass. There's kind of two outliers on this plot. One of them is GX300-4. And if we use the HIDA mass estimate, that actually pushes this over in this direction, which is good. And then AO620-00 is a relatively low mass black hole with a relatively low kick. But there's always some potential that the kick was directed in the opposite direction of the initial peculiar velocity of the system. And so that when you only have one outlier down here, that's not really that big a deal. So I think we're starting to see that the higher mass black holes have lower kicks. Nobody's tried to do this correlation against the spin, partly because we need more objects with better numbers and we need more proper motions, but partly because the modeling is evolving for the spin estimates in a way that it's probably worth waiting a while and seeing what happens when people refit from some of the spins using the updated atomic physics models. All right, so future instrumentation that we need for system parameters. So one thing is we just need ways to get more objects. And so EXTP's wide field instrument would be very good for doing this. eROSITA will probably find some in quiescence. Radio surveys and optical emission line surveys, like Jorge Casares has suggested, those can also find more objects in quiescence. Okay. Next thing is we need more and better spins. And so EXTP, because it has multiple methods to probe the spin, is a really good way to go forward with that. But also probably more model development is needed to make sure that the spins that come out are really actually reliable. All right, and then we need more and better masses for these things. and this can come from big ground-based telescopes. And my hope is that as the 30-meter telescopes go forward, it becomes easier to get a lot of time on the 10-meter class telescopes, which are good enough for making a lot of progress on these things if you can get enough time. And then Jorge Casares has developed this new method where you can get away with a little bit lower signal and noise, because he's shown how to calibrate some diagnostics that you can get using emission lines to give you the radial velocity curves for things where you can't measure the absorption lines very well. All right, and then finally, we need more proper motions, and that's going to rely on very long baseline interferometry and perhaps adaptive optics measurements using ground-based optical and infrared telescopes. All right, so now I want to talk about Strobex a little bit. So the fact that EXTP is going forward, I think, is actually a good thing for Strobex. And I want to just kind of remind people of a little historical fact that about 30 years ago, we were in a similar situation to where we are now, that Ginga had been launched in the late 80s, and Ginga did a bunch of great science. And then the Rossi X-ray Timing Explorer came along in the mid 90s. We sometimes think of RxTE as the satellite that really revolutionized our understanding of accretion physics. But I think it's important to remember that a lot of things that RxTE did were really building on results that Ginga had come up with. And I don't think RxTE would have been nearly as successful a mission if Ginga hadn't been there before that, so that people really had an understanding right from when the time that XTE turned on what the most exciting things to try to do with it were. And so if EXTP launches in 2027 and Strobex comes out in the early 2030s, I think we'll be in a similar situation, that we'll have something that'll do some great science in its own right and then act as a pathfinder. And then when Strobex launches, we'll have a better idea of what are the things that need more collecting area or more observations or more of something that Strobex is able to do that EXTP was either only able to do for the very brightest few sources or just barely able to do when you needed to shrink the error bars down. All right, so I want to talk about some generic considerations. So joint scheduling processes have improved, but it remains a big challenge. And the attitudes and the technical challenges in doing simultaneous joint observations vary widely from facility to facility. So for example, like when ALMA first turned on, a lot of people in the ALMA community had no notion that any targets of opportunity should ever be done. And due to heroic efforts by people, and I was going to say especially Maria Diaz-Trigo, you're now able to do joint scheduling with ALMA and other things, but it's still not possible to do that in one proposal. At the present time, most of the key multi-wavelength facilities are not operated by China, but this could change quickly if the Chinese community pushes for some of the kinds of instrumentation that might help EXTP be more successful. I think we've seen the ability of the Chinese community to go from no facility to something really powerful in a very short amount of time in plenty of other situations already. And hopefully this could, EXTP could drive some other things that could then be proposed for at the same time as EXTP. And also, of course, with the European participation in the EXTP, there may be some easy opportunities to do some joint proposals with European facilities as well. And some of these multi-wavelength things could open up more collaborations with other countries, hopefully even including the United States. And then the low Earth orbit that EXTP will be in gives some challenges and some opportunities for joint scheduling. That when you're in low Earth orbit, you get Earth occultations, which make it impossible to do anything more than about 45 minutes at a time. But it makes it very easy to get some kind of joint scheduling with these interruptions. All right, so in summary, there's a lot of things in X-ray timing that take advantage of either simultaneous or other supporting multi-wavelength data, and thinking about those 6 years in advance could help EXTP have a greater impact. And I think the X-ray binary community needs to anticipate and be assertive about some of these needs, especially for fast timing and good timing calibration capabilities in the optical band, especially because a lot of these things are easy to do if you ask for them in advance and very hard to retro engineer. And there may be some new instrumentation at other wavelengths that's necessary to maximize the science returns.
All right. Is it done? Are you done? Or
Yeah. That was my
okay.
last.
Thank you very much for this great talk, and we cannot clap, unfortunately, but really worthy clap. So we have one question from the QA from Andrea, and he's asking about the current programmatic status of StrobeX. So what's going on with StrobeX? If you could summarize very quickly.
Okay, so yeah, in the US community, we have this decadal survey every 10 years in which panels appointed by the National Academies of Science establish priorities for the next decade. And they are kind of finalizing their report. And then after their report, we'll have a better idea about what they say. What NASA wants them to do is to say either we should have probe missions, of which StrobeX would be, or we shouldn't have probe class missions. They might pick particular probe class missions they think are especially valuable, but there's a pretty good chance they won't make a specific recommendation about StrobeX. If there's a call for probe class missions, then a proposal would be put in for StrobeX, and it could go forward by the early 2030s, I would say. But at the present stage, anything in that kind of size scale for satellite missions in the US side is in a holding pattern.
Okay, so if anyone has a question, they can raise hand that I could open the microphone, or they can write to the QA to question. I do actually have a question.
Emrah, can I quickly interrupt and ask Tom a very brief question? Yeah,
of course. Go ahead.
Tom, that data you showed with the potential correlation between the mass and the space velocity. Mm-hmm. Very nice data. So is there a model prediction which shows a particular kind of correlation one might expect?
I would say yes-ish. So there are some ideas about black hole formation that say that the low mass black holes get formed from supernovae that have a temporary neutron star and then a fallback disk. And whereas higher mass black holes get formed from a prompt collapse of whatever's left in the star, and there's no supernova explosion. So sometimes people call these failed supernovae. And the thinking is that, like, Cygnus X1, for example, has no supernova remnant anywhere near it, and has an extremely small space velocity and a very large black hole mass. So something like Sig X1 may be formed without a supernova, whereas the other systems probably formed from a real supernova explosion, and then some of the stuff fell back. And both the fact that mass is being ejected and the fact that you have a temporary neutron star and maybe have some of these neutrino kick mechanisms, either of those could give you a kick. Yeah. So there's theoretical predictions, but they're vague.
Yeah. Okay. Appreciate it.
All right. Thank you very much. We can have one more question maybe, or we could move on. If there are no other questions. I don't see any raised hand.
The questions, Emrah, can be posted so that they can be relayed to the speaker at later time as well.
That's right. Also, if you type it in the QA, they could be relayed. So I think we could move on now.
Yep.
Thank you very much, Tom.
Okay.
Appreciate it.